Hi everyone. This will be a two-part series. So we'll take it through foundations in the part one, and then in the part two we can discuss more on advanced RAG, advanced evaluation, and latest developments happening in RAG and chatbot side of things. But with the first part, I want to take it into the foundations and then basic discussions. So let's get started. And if you, I just want to establish the agenda before we start. So I'll just be discussing about introduction to RAG and some embeddings and vector databases. And then we have a discussion about a pipeline, how it works in real time. And then we discuss what are the pain points in, enterprise RAG. And then we do a basic evaluation of how do you evaluate RAG system, and then some demo if there is some time, and I'll be sharing few resources as well, so that you have enough time to prepare for the next session where we have all the foundations necessary. So yeah, let's get started.
Just a quick note, Analytics Vidhya has 100 plus free courses from beginner to advanced on topics like machine learning, generative AI, agents, etc. Complete with certification. Click the I button to explore now.
So I hope everyone has heard about RAG, or retrieval augmented generation. But what is it? Where do we generally use it? So we'll just discuss on that. So why does RAG come into play? Like, there were LLMs, you could have directly asked the LLMs, you could get the response. But why do you need RAG? So think of RAG as like trying to limit your context or retrieval phase, where you want to respond or ground your responses to some context, specific context. Instead of asking like a generalized model, you take the help of that generalized model, and then you try to limit your context and get the answer from the specific context. So I'll explain you what I mean by that by walking you through this pipeline. So first thing in a RAG is always some sort of data ingestion or ingestion phase, which can be, the data can be PDFs, documents, images, videos, any sort of data. It can be multimodal, right? So you can pass in any sort of data, and then once you have it, we have something called embedding model. So think of embedding model as something like, you have all the text data or image data and everything. You want to convert it into a one single space or entity where it's represented in terms of vectors. So imagine vectors is just like a set of numbers, where you try to represent your text or image or video or anything in that space, so that it's like a universal space, where you can actually embed, which means like convert text into vectors. And then that helps you to relate each of the text in the vector space. And then once you have your embedding model, and then the input is passed through the embedding model, you have generated your embeddings. You store those embeddings in vector databases. And the reason behind vector databases and not traditional databases is, vector databases are quick and they are optimized just to handle vector data vectors, because of the inbuilt similarity techniques, inbuilt backend just to support the vector storage, and a lot of other features compared to regular SQL or NoSQL databases. And and then once you stored your documents or text in vector databases as vectors, then some user can trigger the application. He can ask a question, he can ask a reasoning, he can ask any sort of query, and that query is also converted into vectors using embedding model. So now we have query and we have the relevant documents in the same vector space. So we can compare the similarity between the query and all the vectors. So think of it like a distance between my question and my relevant answer. So the closest it is in the vector space, the more relevant it will be. So now let's say you imagine that you are able to get some few relevant documents, and then you basically give it a prompt plus your question plus your context, which is nothing but the top relevant documents. So now that the answer that LLM generates will be only present from the text, and not something that it comes up with its own, like it doesn't hallucinate. We make sure that the answer is grounded and it's coming from the document or itself. So that's the main idea of the RAG. And let's see, RAG versus fine tuning. So you might be asking, okay, why should I do RAG? I could have just fine tuned my model. So if I'm working in healthcare, if I'm working in insurance, if I'm working in banking, I would just do a fine tuned model. And instead of using RAG, I would just go with fine tuned model. But there are problems with fine tuning. So because fine tuned model is again like restricted to the data set that you have trained for, and it doesn't have access, or it doesn't get grounded to a specific documents that you're uploading and then asking questions, reasoning, so querying on that. So that's one thing. And then the other thing that RAG helps with us is like, if some new data kicks in, or in real time, if you want to query anything, so that is where RAG might help in. So you don't want to always fine tune for as the data comes in, right? So that is when RAG helps in. Yeah, so having a RAG system is always helpful in terms of search, querying, and retrieval side of things. So as you have seen, just going back, if we have retrieved some documents and then we pass it to embedding models, but we don't pass the whole documents into embedding model. Let's say there's a 100-page PDF. We don't pass the 100-page PDF directly to embedding model, because we can't just store everything in like one vector, because vectors have dimensions and limitations. So and representing and as we increase the dimensions, it's harder even to do search, even to retrieve them in the later stages. So there is this smart technique called chunking your documents and then storing those chunks as vectors in the database. So there are multiple chunking strategies. So chunk is like you have a page of text or chunk or a text where you take that text and then break that into multiple parts in a simple manner. So there are multiple techniques. One is recursive character splitter, sentence splitter, document specific chunking, and so on. We'll talk about I'll just show you about recursive character splitter, and then I'll walk you through each of the technique. I'll give you a high level of what each technique does. But yeah, let's start with chunking strategies. So the basic recursive character splitter will work like this. So let's say this is your paragraph, and I have selected a chunk size of 25, or let's do 30. So as you can see, it's chunking in terms of just like this. As you can see, different colors is chunking accordingly. And we can also set something like, if you have, we can also set chunk overlap. What do you mean by chunk overlap is, if you can see here, there is like a little overlap between one chunk and another chunk. The reason being, we don't want to break the sentences directly in the middle, so that that chunk one and chunk two and chunk three don't have context. So if we are able to chunk and also store some sort of overlap between them, so they will have some sort of meaning, and then while retrieving, we can connect them back. So that's the main idea of the chunk overlap. And this is just to understand the chunking strategy. But yeah, going back again to the techniques. So sentence splitter is something like we would like to split our text based on the sentence. And then document specific chunking would be something like, I want to split based on if my document is markdown or if my document is HTML. I can use tags, HTML tags like H1, H2, H3, body, span, something like that. And then code chunker or splitter, you can write your own custom code chunking strategies where if you're dealing with Python code, if you're dealing with Java code, you can use different strategies. If you're using Python code, you can say something like, okay, there's a def, which is the function definition. There's a return. You can chunk something like that. And you can chunk based on class, or you can chunk based on some attributes. It's completely up to us how you can do that. There are also some code chunkers out there, like there are open sourced, which you can check it out. And then semantic chunking is kind of advanced chunking strategy where it takes one sentence and then compare the to other sentence, how semantically they are good. And based on that, it chunks dynamically to preserve the meaning. And then LLM-based chunking is something that you use LLMs to dynamically and smartly chunk the data. But this LLM-based chunking is very expensive because indeed you are passing the whole text and asking it to chunk. So in real time, LLM based chunking is not viable, and but it might be used in a case where there is like less text, and then it happens in the back end, like in the batch, and it's not in a real time or something. So in that cases, LLM based chunking can be used. Yeah, moving forward. So then comes the basic embeddings and vector databases, just a comparison of how things are in this space. So there are different type of embeddings, like sparse embeddings and dense embeddings. We can just categorize into two as of now. So the difference between the sparse and dense, let's discuss on this. So this is important to understand the difference between sparse and dense. Um, so sparse is like, let's say you are building something on based on keywords, or you have 10 words in your dictionary, just 10 words, and then you're trying to find whether the word exists or not. So you can represent it as like a one-hot encoding representation, where you can say, if my word is present, I will just place one in that position, and then for all rest of the words, I would say zero. So something like a sparse way of describing your data, or for each specific token or a word. In terms of dense, we represent every word in comparison to all words as a vector. So every token will have some sort of, it won't be present like zeros or one, it's not binary, but it will have some sort of numeric representation in a multi-dimension space. Dimension can be of any size, starting from any size to like till 1536, or it can go beyond based on the representation that you wanted it to be. For example, of the sparse embeddings would be something like TF-IDF, term frequency and inverse document frequency, and then BM25, which uses TF-IDF internally. And in case of dense, we can say like a representation using transformers, where we have like sentence transformers as a package, where we can use that to represent our paragraphs or sentences as dense embeddings. We can do that token level as well. And there are some other advanced techniques which are like multi-vector in this case, like Colbert. It's a late interaction mechanism. It's worth checking out. So the idea there is, I don't want to go in depth, but the idea there is that you have this interactions late in the way, so that the computation will be kind of efficient. And then you have enterprise models that you can use like for the embeddings, like from the OpenAI. And then you have small models, medium models, and large models. And you have models from Hugging Face. So all these can be used. It's just up to the use case and the type of the data that you're handling. And is it like working on the scale, or is it just to do a POC? It's up to us to decide which sort of embedding model to pick it on. So now let's discuss on question answer system pipeline. If you want to design something on your own, or right, if you want to just build some question answering system that is based out of RAG, how would you just start? in terms of design, pipeline design. And because there are a lot of code bases you can find all over the internet just to understand, but um, to have a complete flow, it would be better to in better way to understand each and every component of the RAG. So that's why I put up this um, diagram to just explain you the flow, how it looks like. So as you can see, the input text can be anything. If it's a document, it can be a JSON, it can be anything. If it, our input can be like images, videos, which we discuss in the next part for the multimodal RAG part. And we also discuss the advanced version of this. But for now, let's get back and focus on just the text part of it. So as we have the input text, imagine it's a JSON or something, and then we would like to load it and transform it. So we can experiment different chunking strategies here. Like what is the chunk size? As you remember from the previous chunk visualization, I was showing the chunk, right? So you can just say chunk size, overlap, and then there's some other parameters as well based on the type of the chunking that you're using. And so these are some of the chunking techniques that we discussed earlier, right? So imagine, okay, you might be wondering, okay, how do I have a raw document, how do I do a loading and transforming? So there are like different tools that you can use to get the data in a structured way. Unstructured.io is something that you can use to kind of load and transform. And there is llama parse from llama index that you can use. So these are some tools that you can use. Or if you want to do everything on your own, you can always use some external APIs or PDF readers to read the documents, and then and then you have your text in some format, right, like JSON or something, and then you can perform your chunking strategies. So this data ingestion part is huge, and llama index is very good at the data indexing part and the ingestion part of the things, whereas the LangChain is really good at connecting the other things, as we progress, like connecting multiple components from the vector databases and retrieval and then evaluation part. So it's completely arguable, but I would say the data ingestion is good with llama index, and then the LangChain is better used to connect the components. So let's say now we have the chunks, and let's imagine we have 100 different chunks or something. So each chunk of text will be then passed through some sort of embedding model. The embedding model can come from Hugging Face, or we can use some open enterprise model like OpenAI or Anthropic Cloud, or any sort of Amazon Bedrock to convert it into embeddings, the each text chunk into embeddings. And then once it is converted to embeddings or vectors, it is then stored in vector database. So vector databases, we have few easily spun up vector databases, and then we have few enterprise vector databases. So you can use Milvus DB. It's easy to just set up locally for a POC or something like that. And then there are like enterprise versions of VV8 and Pinecone that you can use. And make sure that the vector databases that you're using are supporting hybrid search. So earlier, the hybrid searches were not supported by few, but now I think almost everything is supporting the hybrid search. So the idea behind the hybrid search, I'll just explain you in a moment. But if you remember in the previous slide, I was explaining about the difference between the sparse versus the dense embeddings. So now in the hybrid search, it's a combination of retrieval based on the both sparse and dense. So sparse embeddings are, if you have just initiated the sparse, it will only focus on the keywords. So let's say you're typing something in the Google and it only focuses on the keywords, there should be exact match. So that is when sparse come into the picture. And in terms of dense embeddings, so dense embeddings understands the meaning. So even there's a little synonym or something that you're trying to use and not an exact word match, the dense embedding helps you to get the meaning and get the closest vector. but you want the combination of both. You want to take advantage of both this keyword text as well as vector search. So that is when you have a hybrid search. So think of it something like this. Hybrid search is equals to um, keyword search plus X times or alpha times the vector search, where alpha is your hypertunable parameter. Um, ha- it's a tunable parameter. So basically it varies between 0 to 1, and then you control the level of the hybrid search you want. Either it has to focus more on keywords, keyword search, or it has to more focus on the vector search. So that's the idea of the hybrid search on a high level. And let's say once now you have all the vectors stored in databases, and you started the retrieval process. So, but how do you start the retrieval process? You need some sort of question or something which you have to compare against all the text chunks present in the vector databases, right? So that is when user asks a question, and then we kind of pre-process the question just to make sure the query is correct or not. What sort of question did they ask? Is the question simple question, or is it the question complicated question? Or how do you handle multi-part question? What sort of question type is it? So we can do a lot of stuff over there, like is it a summarization question? Is it something related to judgment, inference, or is it more of um, um, just a simple basic question, or does it have any spelling errors or something like that? So we do spell checks, we do query rewriting if needed. And then there is a technique called hide, which is hypothetical document embeddings. So we kind of generate embeddings based on the question or the query, and then we pass each question again using the same embeddings that we use to store the chunks. If we have used OpenAI, we have to use OpenAI here as well. If you have used some sort of Hugging Face model A or something, or any sort of model, and you have to use the same model because they have to be in the same vector space and same embedded by same model. Now we have the query embedded as a vector, and then we have all the text embedded as vectors. So imagine that you are trying to take the similarity between the query and the relevant chunks, and you have multiple techniques to do that. So this turned into a problem of retrieval, which we have been seeing from ages exist in the system. So everything that we have seen in terms of search and retrieval or information retrieval from like last couple of years, now we have come to that problem. So there are different techniques again in order to do the search. So MMR is like maximum marginal relevance, or we can use another technique called similarity score threshold. So imagine similarity score threshold is nothing but you take one vector and then compare it with all other vector. And then if they are like 80% close, and you compare the same vector with another one, it has only 60%. So you keep a threshold of 70% to eliminate the unnecessary ones. So that's just a similarity score threshold on a high level. Maximum marginal relevance is something that essentially makes sure that um, all the retrieved components are diverse in nature, and not just the repetitions or synonyms of the same output that we got. So it makes sure that the answers or the retrieved chunks are diverse in nature. And next, when we try to fetch k value, right? So what do we mean by k value? Now, let's say there are like 100 chunks in our vector databases, and we don't want to retrieve all the chunks because that is equivalent to searching the whole document. But we want to reduce our search space. So that is why we try to keep our K to a single digit or a double digit to a max. So you can start with something like K equals to 20 and then walk your way downwards like 15, 10, 5, something like that. So the idea is that if you are trying to fetch 20 chunks, you would definitely have an answer. You should answer in that. So that's our assumption. We might have an answer in the top 20 chunks or top 15 chunks. But we will I'll walk you through what are some of the pain points in the next slide. But getting back to this, We can also do something like filtering by metadata. So metadata is something like it can be user metadata, it can be document metadata, or it can be metadata generate. You can use LLMs also to generate metadata while chunking, something like that, where you can store some sort of summary and then use it to filter things. So metadata always helps. Let's say you have a bunch of documents, and then you only want to perform query on the documents that are created after maybe like 2015 or something. So that way you could have eliminated like half of your documents, or thereby reducing search space. So that's a pretty standard example of the metadata filtering. And then there is something you can do with which is called contextual compression retriever, or language token compressors. What I mean by that is you have something called LLM lingua, or other models that actually helps you to um, reduce the number of tokens while we are going to the next step. An ensemble retriever is something that we can combine multiple retrievers. For example, in LangChain, as I was talking to you about, you can use different sort of retrievers and then combine them into like one single retriever. So that's ensemble retriever. So imagine that you're just, instead of just using your PM25 or something like that, you can also use hybrid search. So that's one retriever. And then you have like a lot of retrievers just to do the chunking part, and which are like abstracted in a way, but you can check them in the LangChain docs for the different sort of retrievers that you can use. And now that we have performed the similarity, and then we were able to get our top relevant chunks, our top key values, that would be the context that we pass to our LLM. So LLM here can be, generally in case it can be anything, but because we are using OpenAI embeddings here, if in case we are using OpenAI embeddings, we should be going with the OpenAI as an LLM. But if we have used some sort of if you want to use some sort of open source model, like Llama 3, or using some sort of endpoints for these open source models, we can do basically based on that as well. And then once we have the context, and then we pass it to LLM along with user query, we get output. Imagine the output would look like something like this: our question, the results, and then the source documents. Source documents are from where we have the answers, what are the relevant chunks that are used to get the answers. So we get that in the source docs. And then once we have the answers, we do evaluation. It is like both offline and online. So there are multiple frameworks again, like Ragas, TrueLens, and for observability we have Phoenix and Galileo and other things. So there are some other frameworks also, like Deep Eval, to do the evaluation. But we will talk more on that in the coming session as well, the advanced evaluation. But let's just focus on the basic evaluation for today. So that's on the pipeline part of it. So getting back to some of the pain points that we see in our RAG system. So this has become quite popular after the paper has been released. Survey paper has been released on some of the pain points in the RAG. But understanding this will really help you build better RAG systems. So that's why I wanted to bring this up today. So just to understand, it's the same process: documents, chunkings, and convert it to chunks, store it in vector databases. This is the indexing process. And then while querying, you take the query, rewrite if needed, and then retrieve the respective chunks, re-rank them, and then consolidate, and then send it to LLMs, get the response. This is the querying process. So it's the same thing that I've discussed, but let's see what are some of the failure points, and then how we can have good solutions to that. So let's do one by one. First would be the missing content. Um, you have your documents, you did your chunking, and you store the documents. But let's imagine if the document reading is not appropriate, or the chunks were not properly chunked, or because of some sort of formatting issues in the document there is, or let's say the document is scanned, or let's say document contains tables that are complicated to extract, then you have a big problem that you don't have the data in a right format. So there might be a chance of missing content. So that's what it meant by missing content. So how we can better do it is um, do the ingestion properly, make sure that the documents are properly ingested, the images properly ingested, something like that. And next would be in terms of query process, we saw a problem at missed top ranked. So if you remember, we are retrieving top K chunks. But how do we know that the top K chunks are always in the correct order? So there's always a case like there might be in a random order, or we might have taken only 10, and our answer might be in our 11th or 12th chunk. So it's always a case. So that's another problem, missed top rank. So that is where Reranker helps us. Reranker, there are multiple Rerankers that you can use. So Reranker on a high level, what it does is it makes sure that the answers are relevant, and within the top K, it makes sure that it sorts the answers and re-ranks them by comparing the similarities. So we use cross encoders and other mechanisms to do that. And next one would be, the third one would be not in context. So it's the same thing that I discussed, 2 and 3. We can mix it, like whether its ranked chunks are in the context or not. And then the fourth one would be not extracted. So even with all these things, if we are not able to extract it, then maybe there's like too much context that went into the LLMs. Because of that, we lost the data in the we have a problem of called lost in the middle or something, and the answer was not properly extracted, even though we were able to pass in the pass in a good chunk of text or context. So that's another problem. And for that, we can use some sort of compression techniques. But now I don't think it will be a problem, because we have like the huge context windows, and then we with the GPT-4o and the latest models. And let's think about the 5, which is wrong format. So this is a big problem. That is why OpenAI released something called structured outputs recently. So imagine that you want to always generate output in some sort of structured way, like a structured JSON or something. You can use techniques like prompt engineering, where you just say, this is my output format in the prompt itself. That's one way. And then you can specify the output to always be a JSON object or a JSON response. That's another way. But still, even though being all this, there are still errors done by LLMs to when it comes to structured output. So that's where there are recent advancements using Pydantic output parsers. And then there's now OpenAI supports the JSON mode from like last few months or couple of months or a year. So the idea here is to have an accuracy of 100% with the JSON mode. So that is about the wrong format. And coming to the sixth point, it's about incorrect specificity, where we can use again some advanced retrieval strategies to sort the retrievals correctly. And next one would be the incomplete, which can be just handled basically based on the some transformations that we can do to our input query. And then if you see 8, it says data ingestion scalability. So this is again in indexing processing, right? So imagine that you don't want to sequentially chunk each text and then convert into vector data vectors and then store it in vector database. It's very time consuming. So you can parallelize there. You can spin up multiple workers there to ingest all the chunks at once or in an async way. That's something you can do. And then if you check the 9 structured data question answer, so this is again like if you have tables or something like that, where you have a structured data or we have to query on that. So how do you chunk them better? How do you store them better is something we can focus on this part. And then the complex PDFs are, it might have some tables within a table is a complicated case. So there are, in real world, there are cases like these. So how to handle complex PDFs? How do you parse them well? How do you store those metadata of the tables or complex PDFs as well, is something that they are focusing on here. And then fallback models on the 11th one. Fallback models are something like, okay, like let's say OpenAI or something that I've been using as an enterprise model. So if the model is down, I need to have some sort of router to make sure that it routes to another fallback model, like some sort of open source LLM you can use as a fallback model, or you can use another enterprise model as a fallback model. So that's the idea for the fallback model. And the LLM security is mostly related to make sure that user data is secure, because a lot of information is being processed, which might have the names, credit card informations, and then personal informations. So we make sure that it is handled well, and then uses PII to make sure these are masked, these things are masked and not exposed. So for that, we can use guardrails or Llama Guard, Nemo guardrails or Llama Guard, or OpenAI also supports, I think, the content moderation. So that helps us. So these are some of the pain points that initially were found. And there are a few more other pain points as well as we go through, which I'll cover in the next session. Metrics part, right, which is actually important, and then it's being ignored by almost everyone, because when we build something, we also want to evaluate how good the system is as a whole. So now retrieval metrics are just to understand the retrieval phase. If you remember the retrieved chunks, so we use these metrics to evaluate the retrieval quality of it. So there are two ways. One would be offline metrics, another would be online metrics. So offline metrics are something that we compute in machine learning. Offline metrics are something that we compute locally, and online metrics are something that is computed in real time. Let's say something like click-through rate, hit rate, some on those lines from the user or their feedback, something like that. But all offline metrics are something that we compute on our local, on our side. So something like precision at K. Here the K is the top K chunks that we are retrieving. So if we are retrieving 5, so the precision at 5 chunks, so precision at 10 chunks. So that's the context, right? So we take precision at K, recall at K, FN at K, and we also do MRR at K, mean reciprocal rank, MAP, and NDCG. So the right side ones, MRR, MAP, and NDCG, help us with the order of the retrieved chunks, whereas the order unaware chunks are just like whether you have it or not, just it's present or not. So it doesn't take order into account. So whereas the right side ones will also take the account into the the order of the retrieval. So whether the first chunk is in the first position, yes or not, second chunk is in the second position, yes or not. So that's why having both will help, and also focusing on NDCG would be really helpful, because that is how in real world the retrieval mechanism helps compared as a baseline. And then working on the complete evaluation, which is like retrieval and generation, we have a framework called RAGAS, where we not just evaluate retrieval, we also evaluate the generation, how good the generation is, how relevant the answer is. So there are few metrics in RAGAS that one needs to focus on, like so faithfulness is one thing, answer relevancy, and as you can see, there are a bunch of metrics. So I have attached everything as a link, so you can just go through the RAGAS website, and just the examples are pretty straightforward. So faithfulness score is nothing but number of claims in the generated answer that can be inferred from given context by total number of claims in the answers. So they have a bunch of metrics, and some are based out of similarity, some are based out of LLM prompts, some are based out of just taking a simple similarity and then having a threshold there. So in this case, we have, if we have taken this example, and then high faithfulness answer would be, which is something like this, and then low faithful answer would be something like this because it's wrong, based on the context. So we just, faithfulness score we can calculate based on that. So there's an example of how it is done here as well. And you have all the other metrics as well. So these are some of the important metrics we compute for almost every question answer thing. If you are doing summarization, you can use summarization score. So I think it's mostly based on the sort of how concise it is. And here it is the formula. So they have their own metrics, but you can always build something out of LLM based. And apart from these metrics, you can also drive and design your own custom LLM based metrics, which helps you, for your specific use cases. Yeah, so that is something I wanted to cover. Mm, and I've also attached a collab notebook. You can that's just like a starting point, but you can always find a bunch of notebooks online in GitHub for the RAG, and you can always experiment. But as this is a foundation session, I would just wanted to give you an understanding of how things are, what things mean, and how do you connect multiple things. And and also I've attached another sheet where you have a bunch of resources that you can start when, if you want to prepare get into RAG. You also need some sort of prereqs, LLM knowledge, and then RAG, right? You just can't just directly go into the RAG and looking into it. So I have a whole Excel sheet with all the good resources that you can look into, and that will also help with the upcoming session as well. So we'll be just covering advanced and latest RAG techniques that we can use, and a recent paper that came out called ColPali RAG. We can use RAG based on that as well, and then we will discuss something related to a LangGraph or LangChain Studio, where we can do some simple agent building and then tracing and observability. And then we will go through a agentic RAG with example, which is building a GPT researcher example. So we'll just walk you through, I'll just walk you through these things today. But yeah, let's get started. This is going to be exciting. Regarding let's start with latest RAG techniques. So before that, I think few of the basic things that one needs to understand is chain of thought, action, and what is react. So we all know COT, a chain of thought, and ACT is action, and then action only, and then react is reasoning and action together. So how does this help? This comes under prompt engineering, but this helps us with foundation, and for the future slides, you might need this. So for example, just with the chain of thought, we will not always retrieve the answer correctly. And also with just action, we search, but we could not find the answer because there was no proper reasoning. So a combination of reasoning and taking actions eventually would lead us to a better answer, a better thought process, and better answer therefore. So that is the example here. If you see, if you just go through the example, initially with the COT process, we could not be able to get the correct answer. Whereas with action as well, we could not able to get the proper answer. Whereas with reasoning plus acting, so it goes through multiple attempts, and then finally it was able to figure out the answer is keyboard function keys. So that's one advantage of React, and that's main component as well in terms of LLMs thinking to get an answer better. So that's something. And one of the reason, again, another development in the RAG space, it's been there for some time, was self-reflective RAG. So if you have seen in the last part, where we focus mostly on the retrieval side and an end-to-end pipeline and evaluation, we just covered the naive RAG, how we chunk, how we retrieve, how we rank, how we evaluate, how we generate and evaluate. These are some of the things that we covered in the last session. But yeah, in this we'll be mostly focusing on optimizing those. So self-reflective RAG is like you have your retrieves on demand. So you just retrieve whenever there is a need, and then you also evaluate each of the retrieval in parallel, like whether this is useful or not. So does you have sort of like 4 to 5 critique tokens, like is my retrieval relevant, is my retrieval useful. So you have like these kind of critique tokens, critique outputs for each of the retrieval, which gives you a comprehensive score in the end. So based on that score, you sort the retrievals, and then you understand which one of it, like 1, 2, 3. So this is the order. For example, 1 is greater than 3 is greater than 2. It says that, okay, first retrieval is very useful for us in this case. So that is when we go with the first retrieval. So this is the self-RAG part. You can always read more about the self-RAG part, and it's interesting. And next comes another technique called corrective RAG. So as you can see, our example is X, who's the screenwriter of Death of Batman. And we have some retrieved documents for that, D1, D2, and so on, and so on. We will always again ask our evaluator, is this is retrieved documents are correct to X? In case, like there are 3 options or 3 scoring mechanisms here. One is correct, another is ambiguous, another is incorrect. So based on the type of the retrieved score, correct, if it's correct, then we just decompose and recompose the documents just to focus on the relevant parts of the retrieved context. If it's ambiguous, we also do the same knowledge refinement as well as we search internet or any other resources for extra context. If it's completely incorrect, then we go to external sources like internet and then search it and then get back. So these 3 conditions, as you can see, while the generation part, we have the question X plus K in is the context internal. In case of ambiguous, you have question plus internal context plus external context. In case of incorrect, you have question plus external context. So there are 3 cases where which you can imagine like 3 different flows, one's for the correct, one's for ambiguous, and one's for the incorrect retrieval. And then comes RAG fusion. So RAG fusion is just like you have one query, but let's imagine that you just ask a simple question. When you're trying to embed that question into the same vector space, you can't just get the rich meaning or rich context meaning. So what you do is you take that one query and then generate multiple subqueries or multiple queries out of that one single query, using some template like this on the right. So you're a helpful assistant that generates multiple search queries based on single input query. Generate multiple search queries related to question. Output should be like 4 queries. So now you have, instead of one question, you have 4 questions with a similar meaning from different dimensions. Now you have retrieved documents for all the queries, and then you do re-ranking with reciprocal rank fusion. And then you take those documents and then you generate the answer as you do with normal RAG. So just that we are actually adding more queries and re-ranking to have a better retrieval. So this is another strategy called RAG fusion. Moving on to next slide. So just a summarization or a comparison between different RAG techniques. Again, just look at the key mechanism and we can just go ahead. So in case of self-RAG, again, I told you that they have fine-tuned with self-reflection tokens and critique tokens for on-demand retrieval and generation quality assessment. So it's like we have 5 different reflection and critique tokens which score and analyze your retrievals. So based on that, you will know like which retrievals are important and which are not. And in case of corrective RAG, again, just to summarize, you have 3 different actions: correct, incorrect, and ambiguous. And you will have these are based on confidence scores, and then you will know how good the document quality and retrieval evaluation based on the quality of the document. And then the RAG fusion is another technique where you generate multiple queries from initial query, re-ranks them using reciprocal rank fusion, and then generates the final output based on the final retrieval chunks. So these are the three techniques. You can try it out. I'll also share the notebooks once presentation is done. Yeah, so this is on these latest techniques that you can try. And let's move on to something interesting called ColPali RAG. Now, the basic idea behind ColPali RAG and everything, I'll be explaining you in a little, but this is from the paper ColPali, that they claim that with a standard OCR procedure and then layout detection and then generalized RAG, if you want to do it, it's going to take long at the time of the data ingestion phase, which is 7.22 seconds per page. Because OCR is expensive, you have to understand what sort of document it is. Is it a scan document, or is it a just a digital one? Or then you have to do an OCR in order to extract the text, understand the layout, and then you have to, if it's an image, you also have to caption that image, and if it's a text, you have to chunk those text and then embed them and do all the regular process that you want to do for general information retrieval, or if you want to do RAG, if you want to build a reasoning system, whatever. But the process on the left is always going to be similar. In case of ColPali, they don't generally use OCR. Instead, they use Vision LLM to understand the document. So VLLMs or Vision LLMs are just tries to understand the document structure internally and then query on the image rather than doing all the OCR and layout detection. So that way we save a lot of time at data ingestion. And it's almost like from 7.22 seconds, they claim it's 0.39 seconds per page. That's a huge factor. So before moving on further, we will also understand basic VLM architecture that they have tried to use. So let's understand a simple polygemma architecture on a high level. And so if you see, so there's a question or a query, where is the photographer resting? That's the question. And generally we tokenize it using sentence piece tokenizer and then project these vectors. But now if there is an image, how would you project that into same space? So that is when you have a vision encoder which converts that into vectors, and the linear projection layer, as you can see here, convert that vectors into the same space as the text vectors, which is generated by various the photographers. So now in this case, you have both of them in the same vector dimension space, and that can be sent to the decoder. So now in this case, you have your both image vectors plus query or text vectors together that is being sent to the transformer decoder. And then you have an answer generated in a hammock under a tree on a tropical beach. So this is a standard vision language model architecture where you combine your text plus image to get the output. Now, why is this needed? And what exactly are why exactly is it ColPali? What is COL? So we before discuss, Pali is like polygemma architecture, but what is Col? So before discussing that, I want to explain like what is Colbert, what does it do, and how does that Colbert help us? So you all know about the BERT, and you all know about, we have discussed about in the last session, retrieval and then re-ranking, things like that. But just to give an understanding, what is biencoders, cross encoders, and what is this late interaction mechanism which we are going to use in this ColPali thing. So biencoders are simple to use. The idea here is that you have a query, you have a document, which can be treated as both of them are separate, and then you can index the query and you can also index the document simultaneously, or async. You can do it in you don't need to do it at query or runtime. So document can be indexed offline, like how we have done previously, and then query can be embedded, or query can be vector converted to vectors at the runtime, and then the similarity can be calculated. It's kind of fast and simple. There's no complexities in this. Whereas in cross encoders, you take query and then you compare each token with all the tokens in the document. So it's like you have each token is compared with every other token, and this happens in the runtime. So indexing is expensive. But the problem is that it good thing is that it has a very rich signal, because it knows the context, it knows the query, and it knows how to embed the document as well based on the query. So based on your question, it knows how to document, how to embed the document, and thereby, it captures more rich meaning. But it's very expensive because it has all-to-all interaction. Now, they propose something to handle this trade-off, where you don't want too much of a meaning, and also, I mean, not too slow and not too naive like bioencoders. So they came up with something called a late interaction, where it takes the query, and it also takes in the document, and then and compares the and only takes the last layers, and then takes a matrix multiplication, and then maximum similarity, and then sums it up. So that way you will also get richer signal, which is also multi-vector, and indexing can also be done offline, because as you can see, this is Colbert. We don't want to focus on the initial layers of the query and also on the document. We just focus on the final layers. And for example, we have taken the query and then positive examples of the document and negative examples. And then we take a loss. For a loss, we take negative loss likelihood, and then we calculate the maximum similarity scores. The advantage with this is it's highly scalable, and with contextual interactions. If you see in this case, we can use cross encoders at places like re-ranking, as we've discussed in the last session as well. Why? Because although it's expensive, if you are able to just retrieve top 10 chunks and then you want to filter out 5, you can use cross encoders at those scenarios where you have like limited number of things to work on. But late interactions or by encoders are not that great, but because cross encoders captures more context there. Whereas Colbert is a trade-off between both. You have highly scalable and context and interactions, and you also just work on the last layers. So that's the advantage with Colbert. And then the optimization part, it's actually pretty close to 50 microseconds. So it is production scalable. And so the ColPali people claim that as you can see, the unstructured is a library just to get the text, extract the text, parse the text out of the PDFs. And then BM25 and BG are different embeddings. BM25 sparse, BG is dense. So comparing that sparse and dense on different data sets like archive queue, doc queue, so on, so on. They just created a benchmark, and then performed that BGM3 was doing better here in this case. And now with ColPali, they claim with different experiments, just using vision model, just using bioencoders plus vision model, and then bioencoders plus bioencoder Pali, and then ColPali. So as they have experimented with different techniques, the ColPali outperformed everything by a large scale. They have created a new data sets called Visual-Augmented Vidore, and then they calculated NDCG for all these techniques. So as you can see, there's a huge jump in the improvements, and this is what is being claimed. Okay, let's move on to the demo. So just to give you an context again, so these are inspired from these notebooks, and Biology helps you run ColPali or Colbert easily because it's a wrapper on top of it. So you can use ColPali RAG easily. And then Popular Utils is just an image processing tool, and you need OpenAI just to do a generation part or LLM part of it. And yeah, let's try running and we can go from there. So I've put all my environment variables in the keys here in the collab. You can use if you're aware, and then I can just import them using the user data from the google.collab, and that way I can just maintain everything at one place. And also let the RAG multimodal model, it's coming from the BALD as the package, which is like a wrapper to the ColPali. So we take that pre-trained model and we just call it RAG. It's taking it some time to initialize. So just to get some data on what we want to query, we'll just do wget to download this attention is all you need paper. And then we index that into our database. We can either use a local something like files locally to store our vectors, or we can use any sort of vector database to index the documents and store them. And if you want to query them, you just have to do this. So as you can see, the RAG code has been wrapped up neatly in like 15-20 lines of code because of the wrapper that we have on top. And then as you can see, the results are like the document ID, page number, score, and so on. And you have your binary. It'll take some time to index. But yeah, I'll just walk you through because of the time. And as you can see, once we are able to do a RAG search and we have the results, I'm storing them. I'm storing these results as well. And then, yeah, it's still not defined. It'll take some time. So yeah, and after, and then we'll just see how the data looks like, and then we'll just go forward. So if you can see I just opened the image bytes of one of the image from 8 pages of the PDF. I just opened one first page, and then I saw what is the image being. And then as you can see, the results page has, this is the results page, and then where we have some sort of table and the results. So now we have your query, and then we have the whole page to query on just for the answer. So that is when we can use any sort of language model, be it Anthropic, be it any open source model, open source LLM, or be it OpenAI or any other thing. So for now, for just convenience, we're going to go with OpenAI. And once we have, in case of OpenAI, we just convert that, encode that image into base 64, and we send it via API. And as you can see here, we are just passing the base 64 image along with the query to a GPT-4o mini or GPT-4o, whatever it is up to you. And then we get the response. So for the query that I have, which is what is the blue score, the answer that I got was this. So for English to German, blue score is this. For English to French, blue score is this. So this score indicates the performance of transformer-based model in machine learning tasks, which is actually accurate if you see from the table here, blue scores. So which means that we were able to perfectly get the answers quickly. So and we can also do some testing on local models like Quen or any sort of vision language models that you can try. But the only caveat is that you need to have bigger GPU, larger resources locally to run. Yeah, or else you'll just run out of CUDA or GPU memory. So make sure you have enough, and then you can just run it just like how you used to run transformer models, and then you also get the similar output using the same. And I'll be sharing these notebooks as well with you, so you can also set up your own data and query on those, try a few other things. um, and also you can explore mostly more on the Bialy, the package. It's interesting. So it has other wrappers as well, so you can check them out as well. And this is on the ColPali Vision RAG. We'll focus now on building some agent, and generally we have to consider few things while building any sort of agent. So one would be your tools, second would be reasoning, and then flow. How do you want to set the flow of different flow in the agent pipeline? And then control. Just imagine like control is like a decision thing or something like that. And then verification is mostly in terms of did I get the answer, or do I still have to iterate to get the answer? And then stop condition is just you give a stop condition, make sure it stops. And then evaluation of each of the component or each of the agent level, or at different levels we can evaluate. So these are some of the things that to consider when we are building an agent. And yeah, just even before moving into depth, we'll understand how you want to build a basic agent and tracing using LangGraph. So let me just share you my whole screen, and then we can walk you through a LangGraph example. So for the LangGraph, you can download the DMG in the Mac, or you can use LangGraph Cloud Studio to do that online. So you have to have your project structure in this way, which you can see in this pie chart. You need to have folder like my agent with utils, where you have to put your nodes, state, tools, and then agent.py. And then you have your environment variable setup and then langgraph.json setup. So these are some of the components that are needed for LangGraph to understand how your app works, how your structure is, and then you can spin it locally using this LangGraph application. And then you just have to select it, and then it spins up a Docker for you. Make sure everything is running in the background. It also generates a good, the visualization and flow for you based on the state nodes and tools and agent. By the I mean that based on the structure that is there, structure that is created. So once you have this UI, you can configure everything from here. What sort of model are you using? The API keys and everything are set up. So I can just ask a question, because this is a simple agent, we are not making it complicated. So think of it like I just ask a question, it gives me back. So it's like a simple assistant in this case. But as you scale up, you can build multiple agents for each of your tasks at your company, or if you're building something, think about you want to you want to do a planning agent, you want to do some agent to build some Excel or dashboard out of it. Think about you want to build some agent to understand or transcribe human voices, or an agent to talk to someone over the phone, so based on their conversation. So think about different use cases, and then you can branch out differently based on each of the agent. But just to get back to the simple agent structure, so I would say, hi, can you give me weather in San Francisco, best places to visit here? A simple example. So as you can see, the first step is being executed. And it called Tavily search because in our agent, we have established that you can use internet, you can use Tavily, and also have set up the Tavily API key. So which uses internet to get the, and then it passes that into context into GPT to get the answer better. So as you can see, this is my output. It also gives me the current weather as well as best places to visit. I've added 2 questions. So then it called 2 different actions. One is for the weather and other for the best places. And as you can see here as well, we have the search results coming up. And then the finally, when we have the answer, and that is when we mark it as end. So you can see your run in something called LangSmith. Again, LangSmith is just for tracing, understanding how your LLM thought and what is the flow of the agent and what is the time took for each of the step, and then the number of tokens and cost, everything you can monitor at single place. There are multiple tracing and observability tools, but this is because we are using LangGraph. It's easy to trace with LangSmith. So instead of chat open API, you can always use anything that you want. And also you can check another interesting thing in here is you can check your data sets, create your data sets. And data sets are like, okay, you have run on 15-20 examples now, and then you collected everything at a place. And then you can create your own, customize and create your own charts and do things like that. And also not just that, you can also, let's say you can click one example, and as you can see here, you can also see about the latency, cost, how helpful it is or not, things like that. And then you can create your own dashboards, and there's a playground, a lot of use cases you can do. And then you have your new experiment where you can take your data set and then select these inbuilt evaluators, how concise, how relevance, how coherence. And these are some of the inbuilt metrics that LangChain offers. And you can also create your own or custom metrics based on your use case. So yeah, this is definitely worth checking out, and try building out something using this. I can share some resources to get started on this as well. So this is regarding the LangGraph and building a basic AI agent. And then how can you monitor or trace the run is something that we covered now. So we covered like few simple demo on LangChain, agent project structure, how to spin up locally, and we have said we know how to adjust our inputs, variables, and then tracing. We can also I just showed you how you can use inbuilt metrics as well. And if you want to scale, you have to have the structure built and then the flow built. And as you can see, as you can run, you can trace, monitor, add more metrics, build complicated flows, and build on top of it. And then the last one I wanted to present was an example using is called GPT Researcher. I mean, many of you might have heard. We'll just explore how GPT Researcher thinks, works, what tools it uses. So we'll just go through that. So this notebook is inspired from James Callum work. He's an amazing guy. You have to follow him on YouTube if you want to learn more about LLMs, agents, things like that. So this GPT-4o research agent in LangGraph is something that we are building. Think of it like how Owen is right now, Owen model is right now, but go back and think like with GPT-4o, we are building a reasoning agent that thinks like a researcher. With the tools you provide, it goes and thinks, okay, where can I get the answer from? Did I get an answer from this place, this source? If yes, okay, then I'm going to exit, return the answer back. If I did not get it, I'm going to use the second source, think about it, and then get an answer. So it uses all the available tools it has to get the answer. So that's the main idea in here. So for this, we are going to use GPT-4o as an LLM, and then Pinecone to store our vectors, and LangGraph to build the agentic flow, Archive to just download the papers or relevant papers, and we can access Google via the SERP API. So all these token configurations are set up in here. The SERP API key, Hugging Face token, Pinecone, and OpenAI. So you can also set up your own API keys in there. And let's run this. So as to just give an overview, it has 5 different tools that it can use. It can either do archive paper fetch based on the ID that we provide to just to get an abstract of the paper. We are not looking at the whole paper because we just to keep things simple, but you can definitely. And web search is a tool that provides Google search using SERP API. RAG search with filter, and then the final answer. So these are the different tools that we'll be using. And then finally, we can output our answer in this format or any format that you want for, but for example, we can do it in this format with this specific demo. And let's first download the data set. And we will then see how our data set looks like, what's the format. So ID, title, and then content, because we are looking at archive data set. So, and then we use something called semantic router. This is a package that helps us based on any condition, which route it should take. Or it helps us better, I would say, what sort of LLM you can use based on the different inputs or different queries. So you don't need to always use a complicated LLM or enterprise level LLM for a simple task. Maybe you can have a low cost model to answer simple questions, whereas a high cost model to answer complicated models. It helps in that case. So now we are using encoder, which is OpenAI encoder, text embedding 3 small model. And then we are initializing Pinecone and also using serverless to host it. Because we have API key and everything set up, I believe like, just give me a second. Should be open. Okay. Yeah, we have something called Pinecone. It's a vector database. So whatever you are trying to store using the API in the run in Collab, it's going to get stored in here as an index. You can see here the metric is dot product dimensions. Where's the host, where is it hosted, and then everything as you can see over here. So this is free for some to some extent, and yeah, so you can use that vector database to store your document indexes. And then I'm creating and storing it, but we already have it, but yeah, it's fine. And we are gonna then populate. Now to the main part. Here is where we define our state of the graph, how it looks like. So we define something called agent state, and it has input, chat history, and intermediate steps. So think of it like a state diagram where you have different states, and how we add things to the each of the state diagram, how we reason, how we know when to stop. Think about cases like this. So that is an agent state has like input, your chat history, like if your user have to keep the conversation going to and fro, the chat history, and the intermediate steps to have more context for the agent to get an action. And we also can have our custom tools, as we have seen in the top, archive paper fetch, things like that. So this is just to understand like what's the how tools work separately without being involved in the agent, just to test them. As you can see, we based on simple archive ID, we did a request, and we are getting a text just to check if it's working or not. And then we are using some regular expression pattern just to get the abstract of the paper. And this is how we got the abstract. And then we pack the whole logic into our tool for agent use. So the same logic that you have seen above, we are just packing it into a tool called fetch archive. And whenever we call fetch archive, it uses this function, computes the output, calculates the output, returns the output, and then LLM can decide, okay, whether this is sufficient or should I use another tool to get more context. And then similarly, we have other tools like web search, where we just call Google API to get the answer, or just to get more context. And LLM then judges basically, okay, this is sufficient or not. Similarly, we build the same web search tool. And like, let's say I'm going to skip it, but similarly for other tools as well, like RAG search filter and RAG search. There's like nothing complicated, just because we wanted to use multiple tools. So in this case, in case of RAG search filter, we include a specific archive ID. In RAG search, it's going to just use does query on every paper that is there. So in the data set. So once we have this setup, then we gonna set up a final tool, which is called final answer. And that will return the output in this specific format: introduction, research steps, main body, conclusion, and sources. So we're gonna return that. But now we have all the tools in our place, but we don't have any manager or Oracle or decision maker in our case to how do you connect and how do you monitor the outputs between different agents. And then that is where Oracle comes into play. It's just a decision maker. It's not complicated. It's basically you have initialized it with a prompt saying that you are Oracle, the decision maker. I'm giving you these question, and then I'm providing your tools. Think about it. Use store all the intermediate steps, and then use all the tools, and then get final answer on a high level. So this is something happens, and we're gonna initialize the system prompt, and then we initialize our Oracle. So now when we call a question, or a query, when we do a query and we invoke Oracle, it's going to compute all the steps, intermediate steps. As you can see here, Oracle is something we have input, chat history, and scratchpad that is connected and concatenated with prompt and LLM bind tools. It has it is chained with each and everything, so it knows what to compute, and then it finally gives us the specific output. So for a query, tell me about something about the dogs, it it goes in and calls different APIs. So it just takes in query interesting facts about dogs and then gives us some output. So let's see what it did. Maybe it used web search in this case, but let's see with an additional or advanced example. Now, before that, we define some nodes for our graph. And next we are running the Oracle. So if you want to run the Oracle, we have to define the nodes. So that is what is happening in here. We define the initial states and the router as well to get the final answer. And this is the final code where we know which tools to use. So we just added all the tools at one place, and we tried to use a helper function to convert it into a specific tool with state as an input. And then we define our final graph. So as you can see, this is something like you are defining a node, setting an entry point, which is Oracle, and then you are adding all the nodes. So in the same order that you want them to look like. So you are adding all the nodes, and then you are setting the conditional edges. So what do I mean by conditional edges? Is conditional edges can be something like the ones with the dotted lines. And so I'm trying to plot this. When we try to plot this, so this is what we get. So Oracle is at the center, and then we have all the tools, and it has access to all the tools as well. So it goes and checks for the RAG search filter, or based on its own understanding, whether first it has to do archive search, and then the web search, and then RAG search, and then filtering, and then final answer, or any other order it thinks is better. So we are just relying on a fact that we say Oracle take care of the order, it does it on its own without any without our interference. So again, another example is tell me something interesting about dogs, as we have seen in before. So what it does, intermediate steps, is it calls the web search, does the web search action, gets some output, and that is what is sent to GPT, and we got the output back, which is final answer. And so if you want to build report, this is similar to just output structure, and then we can see how the output structure looks like. Yeah, looks like I ran into some error. Yeah, so this is introduction, research steps, report, conclusion, and sources. So if you want to try on a generalized topic, like tell me about AI. So what it might do is it might go into the it goes into RAG search in this case, and then it also runs again Oracle with other RAG search with a specific archive ID, because it knows from the first step that okay, I know have a paper that is similar to that has AI in it. So it uses that paper to get more context, and it also performs another search, and then finally gets an answer. We can see our intermediate steps here, how it thought. So in case of research steps, it conducted a specialist search using RAG search tool, and then performed a web search, and then got an abstract from relevant archive paper to gain deeper insights. And similarly, we have another question, and then we get an answer. So yeah, the main idea here is that you can always build any sort of your own graph with different tools, set of tools, and then you can have a decision maker on the top that takes that takes care of the flow. But you can also build your own custom agentic workflows. But yeah, as you can see, this is how it performed the research, and then it got the output along with all the report, conclusion, and sources. Yeah.